I want to, well, it's a great pleasure to be here. It's a great honor giving this talk in this celebration of Professor Alberto Verjovsky's birthday. And I want to express my gratitude to him by his intellectual generosity, and I want to express my gratitude to the organizing committee by invitation and hospitality. So the title of my talk is very huge, but I am sure that it's very close from the heart of Alberto, and perhaps it represents the connection of Alberto with physics. So I'm going to talk about this. Well, I want the outline of the talk is after a brief introduction. I'm going to define asymptotic cycles and geometric currents. This is very well-known stuff of dynamical systems, but it will be necessary in order for future reference to construct asymptotic invariants by using quantum field theory. And after that, finally, I'm going to give the conclusions. So the main motivation of this work is a beautiful paper by Alberto and Ricardo Villafreyer, published in Communications and Mathematical Physics this year, where they generalize the Jones-Witten invariants constructed by using a three-dimensional phase theory called the Chern-Simons theory on a three-manifold, compact manifold. But they generalize these invariants, which are invariants of links and nodes, to manifolds with smooth and non-singular vector fields with invariant probability measure. So this very beautiful work was the motivation the main motivation for Führer generalization, which I will describe later. Okay. By the way, these invariants, the Verjovsky-Villa invariants, are new invariants of dynamical systems, and they were extensively described in the book by Arnold and Kessing in this title. So it's a very important work by them. Okay, so as I said before, the purpose of this talk and precisely this work with a former student, Roberto Santos Silva, was generalized the Verjovsky-Villa invariants to higher dimensions by using a topological theory known as the BF topological theory. BF functional, I will introduce this later, or BF action for physicists. So these invariants and the Verjovsky-Villa invariants will be invariants of triplets consisting in a manifold and partial foliation and a transverse measure defined on this defined by the foliation. So these invariants will be invariants of these triplets. Well, essentially there are two cases. The cases of homological trivial flows, when the vector fields are precisely trivial vector fields, generating or giving rise to trivial asymptotic cycles. In this case will be which I going to speak. I want to talk about this in this talk. The other case where it was discussed also by in this work with Roberto and Alberto. For the case on non-trivial topologically few vector fields applied to smooth invariants of full manifolds, and which the last year we sent the paper to the archives. This is the number, which if you like to get. So in this paper, the invariants, the generalized, the Donaldson-Witten invariants for flows are precisely can be regarded as intersection number of fluid flow orbits and constitute invariants of invariants of this triplet, a different triplet, but will be invariants of this. All, but this part is we skip from this part. We will only talk about the trivial case. All the whole construction is performed by implementing the notion of higher dimensional asymptotic cycles, a la Schwarzman, and we use basically the results of by Sol Schwarzman, published in these papers. The first one actually was used by Alberto and Villa in the case of one-dimensional asymptotic cycles, or the case of the Chern-Simons gauge theory on a trim manifold. And in another paper, more recent paper, Schwarzman precisely generalizes the notion of asymptotic cycles to higher dimensions. And then, for instance, for the EF functional and the case of Donaldson-Witten invariant for flows, we use some of the results by this paper, especially more recent paper. We also use some of the notion of asymptotic invariance given in terms of geometric currents by David Rell and Dennis Sullivan in these papers, which I will discuss a bit later. So to start, we consider a manifold with partial foliation defined on it, and this partial foliation is a subset of this manifold of finite dimension. The dimension is n, and this partial foliation, well, in the case of compact case, we can define a finite collection of a disk, a family of disks called the flow boxes, defined on the whole manifold with a finite number of boxes, and we can define also.
But partial means it doesn't cover the whole manifold, like I measured on the
Sure.
edge.
Yes, exactly.
Or even a cycle.
Yeah, exactly.
Yeah.
So this is defined in such a way that the boxes, the submanifolds, the ellipse intersects to the horizontal disk, which has dimension p precisely. Y is a point of this space of this disk. So all of this under smoothness conditions is well defined. We require that there exists also a transversal measure given by a transversal transversal Borel measure given by a transversal submanifold. And we can construct the geometric current given by the triplet, the submanifold, the ellipse L alpha, the transverse measure, and then an orientation of L alpha, defined for each point of this manifold. Okay, so we require also a partition of unity in this compact manifold, and then in this case every P4 can be decomposed in this finite sum, and where omega I has his support precisely in the ETH float box. So, well, putting this together, we can write precisely the geometric current can be defined in this way. We can integrate over this the disk, this transversal disk, the differential forms, and this result will be function on the transverse submanifold, which has a transverse measure, and we can integrate in the transverse space, and finally we can sum overall all the finite collection of float boxes. So this is a real number, and this can be regarded, this is only notation, this is can be regarded as an application of an internal product applies under the P form. Okay, so this in 1975, Roell and Sullivan found that this has precisely a structure of the RAM cohomology, and the current will be using the Poincaré duality. Can be regarded as an element of the homology, dimensional homology group with real coefficients, which determines precisely the notion of asymptotic cycle. So as an example of this, of current, geometrical current, we consider the case of a differential manifold with a P vector field. I mean, P vector field is a multi-vector field of dimension P on this compact manifold. So with mu being the volume N4, the volume form on the manifold, and in this case, eta is like the rho justly of rho over here is an n minus p form, differential form on M. So, but this can be regarded as a contraction operation with this multi-vector field of the volume form. This gives a close. If the flow is incompressible, I mean divergence-free vector field, this the Lie derivative is of omega is 0, so this should be closed. It should be a closed differential form. So The current is precisely given for any beta, and poincaré duality gives precisely that this gives rise to an element of the homology group of the Raman homology group that corresponds to the asymptotic cycle. Well,
This P vector means distribution of two-dimensional vector spaces in time.
yes, it's precisely.
No integrability condition.
No, not necessarily. Well, to simplify the computations, in many cases, it's better to put these vector fields as the product of P. This multivector field is the product of P1 P vector fields, the product of vector fields. So this is a distribution on the manifold, and this is the case more interesting for us. Well, as I mentioned before, we have two possibilities of trivial asymptotic homology cycles that I have mentioned about the D derivative. This is for divergence-free vector fields. This always holds, but the triviality of the asymptotic cycle means that this is omega. This form is closed, but not necessarily is exact. So, in the case of trivial cycles, this form is also exact. Okay, this is another case of non-trivial cycles. Well, in order to introduce the quantum field theory, perhaps the best known example is the reproduction of John's invariant by Witte by using a Chern-Simons gauge theory in 3 dimensions. That this gives rise to the invariance of links and nodes. He starts with a Chern-Simons functional, where A is a connection in the simplest case with of FU2 principal bundle over M. So it's possible to construct the partition function that is the path integral, the Feynman integral over the space of all connections modulo gauge transformations of this theory of action. But the Jones polynomial is given in terms of this computation, in terms of this theory, by the correlation function of the product of capital N Wilson loops, Wilson lines of Wilson loops. The Wilson loops are precisely the homology, the holonomy of the connection. P is the path ordering, and this is the trace over some representation of the gauge group of SU2 in this case. So it depends of gamma. Gamma is a closed trajectory in the manifold, and in the case of the product of n Wilson loops, this gives rise to a link of non-intersecting cycles. And
this link is where? Which, it's in the ambient space
It's in the ambient space of the manifold.
but isn't that, it's for four-dimensional space?
No, it's three-dimensional.
Oh, six, okay.
Three-dimensional. So, well, the computation is a bit hard, and most of this we will use only the abelian approximation, which is precisely the case where this is zero. This part doesn't contribute. Only we will have an abelian connection, U1 connection, and we keep only this part. Well, I'm going to discuss higher dimensional generalizations of this theory. Well, the higher, in this case, well, it's better, perhaps better to define the linking number. The linking number in n-dimensional closed manifold, an oriented manifold. U and B are submanifolds, non-intersecting oriented submanifolds of dimensions p and p prime, given by n minus p minus 1. And we assume that U and B are homological trivial surfaces. So there exists a higher dimensional submanifold from which U and B are boundaries. So the linking number is for the general cases is given by, for linking number of U and B is given by this, where Pi is precisely the intersection of the U manifold with W. So in the most simplest case is precisely when for instance, the case when P and P prime is equal to 1, then the cycles, homological trivial cycles, are precisely the closest trajectories in M, C and C prime, and for instance, we consider R3. And this is precisely the Gauss linking number that is given in terms of this equation, which appears in electromagnetism when you want to compute the force between two circuits using the Biot-Savart law. So in this case, well, the linking number is given by just the intersection of U in this case is C, and B is C prime, and omega is precisely the disk of B. And then we consider the intersection of U and W, and plus a plus sign is given when the orientation of this of U coincides with the orientation of omega. So orientation of omega induced by the orientation of V. Okay, so in this case the linking number is 1. The higher dimensional generalization is this formula holds, and for the case of Rn, this admits a beautiful general formula that I will mention right there. So the theory that we consider here is the BF theory. BF are not the initials of some names. This comes from the letters in the action. You can consider a B field. B field is a P form in this case, and this can be in general the curvature. The F DC could be F, being the curvature of possible subconnection in here. In this case, C will be a P prime 4, precisely P prime is n minus p minus 1 form.
Why BF? Why they call BF?
Well, by the letters in the action. This action has not the names of some people. It's only by the names by the letters that appear when some people initially write this action. But actually, this action is not new. In the 70s, García Plebansky, a professor working in Simestab in Mexico, from Polish nationality, he found a theory of gravity, which is precisely, it has the form of a BF theory, plus some constraints, some additional constraints that give rise to the dynamics of gravity, the self-dual gravity, and then we can find the gravity theory, the dynamical degrees of freedoms. So in that case, B was a 2-4 was related to the tetrad, but there is a beautiful review by John Weiss about this, and the degrees of freedoms of the gravity in that case was not the metric, but this form and the connection, the spin connection of the theory. Well, this is just a comment, but in this case we consider the case of this BF action, and the equation of motion, the classical equation of motion, are given by they are closed forms. So the non-trivial ground states are precisely the model space of the space of solutions are the product of cohomologic, the random cohomology groups, as you say. So there is some notion of symmetry. This action is invariant under diffeomorphism and also under gauge transformation. This action is abelian, so the gauge transformation are very, very simple, and they are given by where B and W, little b and W are arbitrary p minus 1 and n minus p minus 2 forms. Okay. This is a classical treatment, but this is a naive quantization. Well, this is a naive quantization. The right manner to quantize is by using the Batalin-Vilkovitsky formalism. There's a copy of paper by Alberto Cataneo, but this way of quantizing the theory will be sufficient for us, for the object of this talk. So the important object to compute in quantum field theory is the correlation functions, 2-point correlation functions of two observables O that are the operators of the theory, and this operator are Lorentz invariant and gauge invariant, are invariant quantities under the symmetries on the gauge symmetries of the theory. So we can compute the correlation functions are given by this path integral, integrate over all B fields. Well, this is integration on the space of all B's, of all the B and C forms. So in the previous papers I mentioned, Horowitz, Renicki, Blau, and Thomson, George Blau, Matthias Blau, George Thomson from ICTP. They found that this 2-point correlation function, for the specific correlation function, is precisely the linking number of I mentioned before. So, in the case of, for instance, when n is odd number, and c is b, in this case, p and p prime has the same rank, it's the same degree, so we can put this condition. And in this case, we get the self-linking number. And for instance, for the case, it is given by this. In the case of M is Rn, the linking number has a very nice form, generalizing the Gauss linking number. This was done by Hugo in this year. Okay, so we want to then to find, using the BF theory, we would like to find the generalization of Verjovsky-Biel invariants. So in this case, well, we consider higher dimensional asymptotic cycles and use quantum field theory to proceed. So we can one of the okay. Okay, we start from this equation, and we consider observables which are related to asymptotic cycles. I mean, the manifold, underlying manifold, has a multi-vector field or a family or various multi-vector fields of different dimensions. And the only change in the path integral will be the observables. We want to change this observable by asymptotic observables, asymptotic observables, and we proceed to compute the path integral in this case. The vector fields underlying the manifold will not change the nature of B and C degrees of freedom. So these vector fields are like background fields that are not dynamical. And we, in this case, it's not necessary to introduce these vector fields as additional degrees of freedom, physical degrees of freedom in this part. So it also doesn't contribute to the Lagrangian. So the Lagrangian will be the same of BF theory. So we proceed to compute precisely the correlation the correlation function. And in order to do that, it is necessary to make some additional statement. For instance, to use the fact that the Hodge's decomposition theorem and decompose a P-form in terms of harmonic, satisfying the Laplace-Beltrame equation, and longitudinal, I mean forms which are the differential, the exact derivative of some form, and the co-differential forms, which we call longitudinal and transversal parts So the integration over B is given in terms of transversal, longitudinal, and harmonic forms. This is for in general. Now, the transverse part, it is a very well known in quantum field theory that if the theory is abelian, so the ghost in the Fourier-Popov quantization, the ghost factorized, I mean the longitudinal degrees of freedom factorized and can be cancelled out in the quotient by the normalization. So the only degrees of freedom that contribute to the integration are precisely the transverse degrees of freedom. So the asymptotic cycles, which will be invariant, the asymptotic observables are precisely given in terms of only transverse forms. So the forms that enter in this computation will be only transverse in the case of over here. So, but in the case of if lambda is eigenvalue, lambda square of the Laplace-Beltrami operator of this equation. So lambda different from 0. So the case of harmonic forms doesn't exist. So any P form is composed just in terms of transverse and longitudinal P forms. So we can find that there exists precisely an operator. This operator constructed for lambda different from 0 with the exterior differential and the Hodge operator, which maps transverse P forms to transverse n minus P minus 1 forms. And this is can be obtained that it is precisely an isomorphism. This will be very necessary in order to compute the Feynman integral. We consider also basis, orthonormal basis for P forms B and C, satisfying this satisfying this metric in the space of differential forms is given as usual, and the fact that this is an orthonormal basis is give rise to the delta ij. Okay, using precisely the isomorphism, using these operators, we can find a relation between the C and B forms, and we can express the C form in terms of P forms given by this. This is precisely an n minus P minus 1 form, and this is a normalization factor in order to find it's a normalization factor that ensures that C is an orthonormal, is also orthonormal. Okay, so in this basis, finite basis of forms, B and C can be expressed in terms of this linear combination. So the action, the BF action, is after the computation is given by in terms of the coefficients of the expansion, and lambda different from 0 is given by this. So the integral in the computation, the integral of this integral is a Gaussian integral. So after some transformation of the coordinates, so we can integrate very easy and find that the linking number is given by by this expression. So we are computing here the case of one of the observables is an asymptotic observable, and another one is just a normal standard observable. So in this case, well, and the fact that n is an trivial homologous surface, and this gives rise to a trivial asymptotic cycle. We can express this expression in these terms. So the triviality implies that this is an exact form, so we can express the above relation, the above equation by this. There exists a W that we can express that. So, and we use the fact that the isomorphism that relates the B and C forms in these terms, which we substitute here, and finally we will have one this expression. So okay, these degrees of freedoms, B for B and C, are only transverse degrees of freedom, but since they doesn't contribute to the integration, to the path integration, we can add the longitudinal and harmonic forms in order to complete, to get the completeness relation in terms of deltas are multiplied by the volume form of this product. This product is the volume form of the manifold. So we can compute, find the final expression is given in terms of this alpha. Alpha prime is a normalization number. It's not a normalization n minus 1 minus p minus 1 form, which express the differential, the triviality of the asymptotic cycle. Is in terms of this is precisely that this is equal to d alpha or d alpha prime, where alpha prime is given by this. So this link number depends on the flow and on the measure. So this is precisely a number obtained by Kostick and Vogel in this paper for the case of n equal to 3 and p prime equal to 1. So we were able to generalize this number for higher dimensions. Another case is the cases with the flows, and then we can consider two asymptotic observables for two fluxes, x and y, and consider two measures, invariant measures in the manifold. The computation is more or less the same, so we can find at the end of the day, we will obtain a linking number of these fluxes, of the flux x and p, given by in terms of integration over m of these forms, which express precisely the expression Hopf-like invariant of the intersection associated with the vector fields. And in this case, precisely for the case for P equal to 1 and P prime equal to 1 also, in the three-dimensional case, this result was obtained by García and Chekhov in this paper. They want to find the equations of magnetohydrodynamics were interpreted in terms of ergodic terms, in terms of average linking number of two vector fields. So in this case, we find in a natural way this a higher dimensional generalization of García and Chekhov results. Okay. And the self-linking number is obtained by making precisely the fluxes equal x and y equal. And in this case, we obtain the self-linking number given by this. Precisely the Verjovsky invariants are, after the computation, are the exponential of these numbers. A Hopf invariant in higher dimensions, greater than 3 dimensions, that appears in the book by Gordon 2. And for n equal 3 and P and P prime equal to 1 is the classical result by Arnold. This number is called asymptotic Hopf invariant or helicity, which has a very nice interpretation, description of some applications in astrophysics, for instance, in plasma, astrophysical plasma in galaxies and stars. So, before I finish, I want to give there is a generalizer linking number when we couple a connection for instance edge-to connection on in this vector, this principal vector bundle over M. So the A is a flat connection. So the generalization of the linking numbers is given precisely by this. Where this part is precisely, there is a set of trajectories connecting points of x and y are points of the two cycles. Sorry, this is the cycle U. cycles. And this is in the case of we have no connection at all. We recover the original linking number, and I write this invariant by the following. In the case of string theory, derivation of asymptotic. There is a string theory derivation of asymptotic observables. In string theory, well, in 10 dimensions, well, M will be a 10-dimensional manifold. Perhaps Lorentz metric 9 plus 1 dimensions, and there are two actions coming from the John-Simons topological part of the action for two types of theories called type 2A. B2 is a B field, which was B field, and F4, in the case where there is not an intersection of manifolds, this is precisely curvature of a C3. C3 is a Ramon field. They are differential forms of degree 3 and 2. So, okay, so there is another type 2B theory. And in this case, we have C4, H3, F3. H3 is the curvature of P2, and C4 is a form, Ramon form. In string theory, we have different forms on the whole 10-dimensional manifold with different degrees. So, a very interesting thing is when okay. Well, just 1 minute for finish. Well, in the case of we consider, for instance, this is a very heuristic argument. We can have the case of two events of Bohr volume omega p on another not intersecting event of a dimension p prime. So we can compute precisely the brains. And usually there is between these brains there are open strings connecting these brains. So we have precisely this situation when this trajectory, this gamma trajectory, will be substituted by the open strings with coping with the B field, and we can obtain precisely the generalization of this generalized linking number. So there is a lot of things that we can compute in this theory. One of them is the generalization of homogenic invariants, and one of the one of the interesting aspects is that this the chart has a chart, Ramon chart, that is taking values not in the homology, but in the K theory, the topological K theory. So we need to generalize the notion of asymptotic cycle in terms of some asymptotic K theory. And for this, there's a paper very nice by Judith Baker, precisely speaking about the K theoretic invariance for system algebras. And this is one of the things that I would like to address in the future. Thank you very much, and I'm sorry about it.
Questions to the speaker?
Yes.
Bueno, Witten usó para teoría las ecuaciones de Jarvis la ley física que generaliza el límite en altas dimensiones está contenida en las leyes de Jarvis.
Then, can you give a repeat the question, please? I don't understand very well. Yes, yes.
Sí, Witten usó para sus invariantes las ecuaciones de Jarvis.
No, Chen Simons. Is lower. You have not Jaginess, but the theta term, the contracting term, and you reduce to the boundary of 4 manifold on 3 manifold, you will find precisely the Chen-Simons term. So it's a bit like the Chen-Simons is like the theory defined on the boundary of a 4 manifold. Yeah. Yes.
Yeah. So is there a interpretation? I understood very little of your talk. I think one thing I understood is that 2-point correlation functions can be used to calculate linear numbers.
Yes.
Asymptotic cycles, well, classical as well as asymptotic. Just a very naive question. Is there a similar, or is there some kind of geometric interpretation of endpoint correlation functions? Is there a similar thing?
Yes, well, no, even in the case of normal case, the computations, when you use a topological theory, is independent of the dynamics of the metric, for instance. It is a topological invariant. It could depend on the complex structure of smooth structure, differential structure, but it's independent of metric. So this,
But is there some naive description of it? Like, I mean, here in the 2-point case, I mean, I understand what the linking is. You have two homotopically trivial curves. And,
in this case,
is there like a topological?
It's a geometrical interpretation of this.
But for endpoint functions, you don't have such a naive geometric interpretation.
Well, I think it's more or less the same that the computation by Witten in this case. You have a endpoint correlation functions.
Oh yeah, okay.
You have something like a link.
The number of components of the
The number of components of in this case, the number of components of manifolds.
But for a flow, you have an infinite number of components, like a diffuse knot.
Right. Thanks.
About 2-point correlation function.
Yes.
You mentioned that is the formalist.
Formalist, yes, it's the right.
But that formalist gives you the quantization in terms of the Fock space. But can you actually do the calculation of the formalism?
No, not necessarily. This is one of the ways of computing the manifolds, but you can use the path integral also. Not necessarily using the Fock space.
And for the calculation, you you can do the calculation with the string theory you mentioned?
Yes. This is just an heuristic.
Riemann charge?
The Ramon yes, it's the path integral is very complicated to perform in this case. We need to understand better the geometrically and topologically in order to say something, because to perform the path integral from first principle will be very complicated.
Thank you.
Okay, so let's thank Hugo again.
And,
And that was the total of the conference, so I think just in the garden.
No, first, I think